Yeah, so I have the same slide that Gerald had, so soak it in, feel all legal and stuff. Okay. All right, so sorry my talk has a really long title. What it's about is a device that we just announced and put into production last couple of weeks ago. And it has 9 100 gig ports. Each one of those ports can be subdivided into individual 25 gig interfaces as well. It also has 9 PCIe interfaces. So if you think of 9 Ethernets on the top and 9 PCIes on the bottom, the idea is to be able to maximize how much I/O you can put into an IA platform, or into any CPU platform. And in the middle of all of that I/O, we have a frame processor called FlexPipe, which is a programmable, flexible pipeline to look at packets, modify packets, count packets, mirror, all of the same type of functions that you would see in OpenVSwitch. And then lastly, which is I think pertinent to what we're talking about here, is we want this device to be compatible with all of the different open standards that are out there, so that you don't have to use an Intel-specific driver, or you don't have to use something that's Intel proprietary in order to take advantage of the features. And we have another talk later on today that's talking about the generic interface that we'd like to see for this type of device to be able to do some of the interesting functions we want to do with OVS. And so that's what Red Rock Canyon is. We call it an Ethernet multi-host controller, but it can be used in a lot of really different and interesting ways, depending on what your form factor is, what your use case is, these types of things. And so, what we're trying to do with this new device is two things. The first thing, we want to augment the packet processing that's going on inside the server. So we've pushed switching as close as we possibly could up against the CPU without being inside the CPU itself. And we wanted to snuggle up there because we want to speed up what's happening on that CPU and optimize it. And so what the result was that we can reduce a lot of the I/O latencies that are involved with getting packets in and out of the system. We can reduce how much time it takes to process a packet before you push it into the CPU or into the VM. And we want to be able to chain all of these functions that are running inside of VMs together using SDN. And the second result, because you have all those ports, all those Ethernet ports, all those PCIe ports, you can come up with some really interesting form factors. And we sort of leave that up to the customer to say, well, okay, how do I want my system to look like? And maybe it's a system that looks different from your regular white box server, or maybe it looks exactly the same as your previous server. It just has these new functions inside of it. And that's where we land with these two kind of major form factor classes. We call the multi-host modular server platform, which you can attach inside your platform. You might have a PCIe backplane or an Ethernet backplane. This device can do both. And then you have some number of uplinks that control it. And then when you have multiple hosts, you have that 9th PCIe interface can be used to have sort of an N+1 management processor to be able to share all those resources that are all being interconnected at the same place. Or you can just use this device on a NIC card and treat it like a NIC, but we call it a software-defined infrastructure adapter. So it's trying to make your infrastructure more software-defined by giving you a lot more knobs to be able to control from software how the packets go in and out of the system. And so what we're focused on is to be able to drop OVS on every one of these CPUs and allow that OVS to be able to take advantage of the platform. And some of the advantages you have in these different form factors is first off the 25 gig SerDes that on every single Ethernet SerDes on the system, there's 25 gig capable. You can also go back to 10 gig and 1 gig and all the different speeds in between. But this is sort of a really important flexibility to have, is you can use your maybe not existing copper cables, although some of them do work, but your sort of existing infrastructure and just have it go 2.5 times faster. An interesting function that we were able to perform is that normally you'd have your NIC on one socket, and then the other back socket kind of, if you need to get packets to it, you send it over QPI. But with multi-socket, what we can do is when the packets come into the FM10K, we classify which socket the packet should go to, and then send it directly to that socket, avoiding that QPI hop latency, and also. Instead of having to have your packet be, proxied through the first socket, you completely avoid that. And so for virtualization, when you're dropping VMs on this system, you shouldn't have to care if it's on socket 0 or socket 1, just like we were talking about in the previous presentation about CPU pinning. Now you can just, directly send it to the socket that you need it on. And then if we can do that for sockets, we can do that for hosts too. So if we have multiple hosts on the system, inside the FM10K, we'll figure out which host the packet needs to go to and deliver it in directly. What we can also do is, for multiple hosts, if we're attached over PCI Express, we can direct the packet to a particular queue on a particular host. So we have a lot of control over where that packet lands into the CPU subsystem. And so, the two main use cases that we have for all of this forwarding inside this device is first in the infrastructure, where we want to be able to realize the dream, which is to be able to virtualize the compute, virtualize the network, virtualize all the services in the system, and then string all the services together with a service chain, and have that be really efficient, and not have the intelligence that's doing all that stringing together be the bottleneck. And so one of the functions of this device is for it to be able to natively handle service chaining headers like Genev and NSH. The second use case is actually inside the VM or the container. If I have this classification capability available to me, and I'm sending packets to a VNF, I might want to spread that traffic to the different queues or cores or threads or processes inside that VNF, so that step doesn't have to happen in software. So it allows me to take a VNF and scale it all the way up to 100 gig if I wanted to, because I'll be able to do this traffic distribution either using a hash like RSS, or doing something more intelligent with a classification to say, send all of my traffic of one type to one queue, and the other show the traffic to these other 5 queues, this type of thing. And also within the VNF can tell me, hey, I don't want to see any HTTP traffic. Just drop it and tell me when you see it. And that's another function that we can offer, not just to the CPUs, but to the VMs that are virtualized inside of them. And so what we're doing with OpenVSwitch sort of unmodified is two things. First, we want to be able to support obviously the kernel and the user space data paths, but we want to be able to support them simultaneously. So if you have a classifier in the hardware can say, well, all the ARPs and control frames, send up through the kernel. That's where they should go. But these, high priority, high latency sensitive flows, send them into the DPDK pipeline because I know that they can be, fully handled by that pipeline. And so this flexibility allows you to sort of have like a table zero in between the two different net devs, to pick which kind of infrastructure processing you want to give it. The second thing we do is, very similar to that we do with all of our other devices, is we take advantage of all of the DPDK sort of like expert mode functions that you can do to make these things go faster. So we have a vectorized PMD that uses some of the the vector instructions of the CPU to do faster processing inside the user space pipeline. And we obviously take advantage of all the stateless offloads, but we also take advantage of them while in the presence of tunnels, which I think was talked about earlier today. But what might be interesting is if we could use that flex pipe that's underneath and actually introduce that into OVS. Say, well, okay, well, we did sort of all the basic things that you can do with OVS to make it faster, but what if you had a pipeline that sort of looked like this, where you could do wildcard matches, exact matches, tunnel NCAP, decap, and some amount of QoS to be able to shape that traffic, to protect some of the VMs or the containers on the system. So, for example, we could use our TCAM table to do service function forwarding. So we could use the classifier in the system to classify either sort of a bare packet or a packet with an NSH header, and then forward it to wherever it needs to go, or NAT it across to the next server across the data center. We can do that with the TCAM that's inside the device. Or we could just do a basic wildcard, just to match on a TCP field and do some special handling. Or if we want to say, well, all the iSCSI traffic should be on this QoS priority, we could do that with TCAM. We have something called the multipath table. We have an L2 and an L3 multipath table. This is similar to what was talked about in the NAT discussion, is that after the classification, we can say, well, I want to forward this packet to these 25 different possibilities. And then I'll take a hash across those possibilities, and maybe one possibility is an NCAP, one is a route, and one is a forward, one is a trap. So the multipath table gives us that traffic spreading function, which we can also do across cores, CPUs, and uplinks. So it's a really useful function to have in hardware. It's sort of like a super RSS. And then our tunneling engine has a big exact match table that will match sort of the inner header of the packet and then decap it, or it will match the packet, exact match the packet and then NCAP it in the other direction. And then we have some QoS functions to basically do rate limiting on VMs. So one VM can't take all 100 gig of your uplink, and we have different classes of service so you can separate your data and your storage traffic. Okay, so we have all these cool toys in the hardware. How could we kind of up-level that into OVS, and how do we do that in a device-agnostic way, so that if there are other devices that can do the same thing, they can come in and use the same interface. So we sort of have two different functions that we're looking at. One is just we just call generic data path acceleration, and it seems like the easiest one, the biggest bang for your buck, is just to accelerate that wildcard match table. So what we do is when the packets come in, we match them in that TCAM, and then as a result, we'll set a metadata field in the descriptor of the packet. And then OVS, if OVS is aware of this acceleration, we'll say, okay, well, you actually matched on something that I told you about, so I'll just look that up I'll just index that into a table as opposed to having to do a complete wildcard match in software. And we think that this might actually have a pretty big impact. It seems to be the next bottleneck. After you're running the DPDK netdev, after you've optimized packet input, packet output, being able to optimize wildcard matching seems like the next thing to do on the list. And not only can you set metadata, you could drop packets, you could count them, and you could also mirror them. So you may want to say, well, all the packets that are coming in, I want a 1/1000th of the packets are sent to this VM, or they're sent in this tunnel across the data center. You can do that in the device, and so it's sort of, you won't have these sort of funny cases where it's not working, but then you turn on the logging to figure out what's wrong, and then the problem goes away. when it's happening in the hardware, it sort of happens automatically without changing how the software is working. The second acceleration that you could use is to have the device do tunnel NCAP decap for you. So you could say, well, I'm going to program in the device. When you see this header, please remove the outer header and tell me which tunnel it came in on. Thank you very much, and I'll process it accordingly. Or in the other direction, you could tell it, when I send you this type of traffic, please put an outer header on it and ship it out. Cool. And the last thing which you think is pretty interesting is we might be able to accelerate multi-queued VirtIO. So one thing that you had before you virtualized was when you sent a packet to a VM, you used to be able to use RSS or flow director to spread that traffic into the right queue. But when you do NCAP and decap and run everything through software, you have to reestablish that RSS or that flow director function. But we'd be able to do that in hardware and then deliver that packet basically directly into the VirtIO queue just by mapping hardware queues to VirtIO queues. And then I guess the last step of that is if you're already accelerating the TCAM and the tunneling and basically forwarding the packets directly into the VM, why don't you just have OVS Control SRIOV? And so how this works is we preserve OVS as the control point, and by default, every packet uses OVS. But all of your flows that are sensitive to latency or performance, you push them into the hardware, and then the hardware can directly pass that packet right into the virtual function. And what's nice about this is it gives you really consistent performance. The performance won't change depending on how many TCAM entries or how many tunnel entries are in there. Whether you're doing mirroring or not, it's very consistent, which is slightly different from software where sometimes you get loaded up and you fall behind. So, an example we run in the lab is, with Nixia, we'll send in VXLAN tag traffic. We'll layer 3 forward it in DPDK and then send it back out. And we're able to do this at 100 gig speeds because the layer 3 forward is just running in a VM. It has no idea that it's behind OVS. So OVS control is preserved, but we're running at just sort of totally unreasonable line rates because we're using a combination of OVS and SRIOV. And so, in summary, we can achieve these 100 gig line rates, and then not only can we have a 100 gig line rate, but we can also scale our VNFs to 100 gig as well, because we're able to do these traffic spreading functions so that you can have a multi-core efficient VNF. And then we want this to be compatible with all the control planes that you already have, because it wouldn't be worth it if you had to rip out all of your software because you wanted a slightly faster environment. So that's it. And this is a summary slide of what the device is. Cool.
Let's thank our speaker. So we have time for questions. So if you have a question, please come up to one of the microphones on one of the sides of the room here.
So for the multi-socket configuration and multi-host configuration, how do you do multi-socket? Does it appear as a different PCI function on each socket?
Yeah, it does. So there's a different PCIe function on each socket. And then we have a separate set of netdevs that abstract the uplinks. So when you send a packet, you don't send it on the PCIe device attached to the socket. You send it on a different netdev that's attached to the 100 gig. So you're just sending and receiving at 100 gig. You don't really know or care which socket it's on.
Okay, and how about multi-host support? Is that like MRIOV?
It's not MRIOV. Okay. In multi-host, each individual host is unaware that there is a layer of switching above it. So all it sees is a single PCIe device coming out of it. And then when that packet is sent, then that's why there's that N+1 processing interface. the control plane processor will then sort out which uplink the packet should take coming out of the system, or if it should go back into some other host.
Okay.
I don't know who was
It's a
first.
race condition.
He was there first.
So you mentioned that you wanted to put like high priority flows into the flex pipe and your FM10,000. Is there some sort of resource limit that prevents you from putting all the flows into it, or putting as many flows into the hardware as you would in, say, the OpenVSwitch kernel cache? And if not, is there any way to get beyond that limitation, or if there is?
Yeah, there are definitely hardware limits as the size of the tables. So essentially, when the hardware tables are full, that's why OVS is the default. So as opposed to existing SRIOV, where it's sort of all or nothing, when you have OVS acceleration, what we can do is we put as many rules as we can into the hardware as if it was a cache, and then everything else goes back into OVS.
So I'd like to put in a plea for two things. One is supporting caching behavior, so you could use it like the kernel cache, and two, thinking about making bigger flow tables, because they would really help realize the potential of OpenFlow and SDN.
Okay, great. Thanks.
So then where are you actually hooking into OVS? Are you going in like the kernel data path and translating the flow IDs into filters that you push down, or are you going up higher into user land, or where are you actually doing it?
We interface with userland. It's a user space interface, and I think the next presentation is on the interface that we're sort of proposing.
Thank you.
Cool.
Okay, I have a request. There was,
Yeah.
Could you go back toward the beginning? There was a slide I wanted to look at a little bit more. I think it was only maybe the second or the third slide.
This is the second slide. This is the first
Oh
slide.
gosh, go forward. Go forward.
This one?
There was one. That's it. I want to get a photo of this slide with more OVS logos than I've ever seen in one place.
I could have made
before.
OVS bigger, but it didn't fit.
Yes, thank you.
All right,
Do you have any final remarks?
No.
Oh, we have one more question.
Yeah,
Yes,
go ahead.
please go ahead.
So the preferred way on the kernel side to actually deal with this is switch dev. So do you have any plans in participating in switch dev development and making this using switch dev infrastructure?
No, I think that this is completely different than switch dev. So,
Why?
We talked about putting this into switch dev, but we thought that it got a little confused with what's happening on the top of rack switch. And we wanted to make sure that they were somewhat separate, because switch dev, I think, is exposing the hooks that you need and able to run a control plane on Linux. Well, this is exposing the hooks that you need to be able to program the data plane in the switch. And so it's awfully different in subtle ways, and so that's why we wanted it to be separate. But yeah, we have been part of that switch dev discussion, and I think we're trying to get together some agreement on what's the right way to abstract these types of pipelines underneath a really powerful flow-based solution like OVS.
Okay, let's thank our speaker one more time.